I'm Dragan Savic, representing the Water Distribution Systems Analysis History Project. The purpose of this project is to document the history of water distribution systems analysis. An important part of the project is a series of interviews with engineers, modelers, researchers and practitioners who have made significant contributions to the field of water distribution systems analysis. Our interview today is with Professor Ezio Todini. He has been in the forefront of water distribution systems analysis for over 45 years and continues to make significant contributions. The interview is being conducted on the 2nd of September 2015 in Leicester, UK, during the Computing and Control for the Water Industry conference. Ezio, you have been working in the field of water systems analysis for a number of years. Can you tell us how you first got involved in this area?
Well, Dragan, I graduated in 1969 from the University of Pisa as a hydraulic engineer. And I could not find a job until I was enrolled by IBM, where I started working as a research assistant in a research center in Pisa. At that time, we were doing a lot of work in hydrology, and I was obliged, and I thank IBM for that, to learn a lot of things that I never heard of in the university. That is matrix algebra, numerical analysis, optimization, and statistics. And with all this background, I started doing research. And then I got a course at the University of Pisa. I was lecturing applied hydromechanics. And I read a paper from someone in Italy who demonstrated that the cross method in water distribution network sometimes converged and sometimes didn't. So I wanted to try using the techniques I just learned, like numerical analysis, to apply globally to a nonlinear system the technique of the gradient. And I just did it. And I wrote a Fortran code to demonstrate my student that using the proper approaches, it had to be convergent because it was a convex hull. And funnily, it came out that it was so fast. It was a very fast code. But, you know, things, I was not working full-time in water distribution systems, so I published it in a local journal in Italian, and nobody knew about it, not even the Italians.
So much of your early work was done while you were working in the industry, say IBM, and then working at the university. Can you tell us more about that early work?
Well, the early work was mostly experimenting. We were paid to do research, and I had very little work to do at the university. I was only lecturing, so I concentrated myself and I experimented things like Kalman filters in the early 70s, where people didn't know really what was about. And also I worked in some Bayesian stuff like decision analysis, and then we also worked on two projects which were very interesting. One was the Lake Nasser optimization, and the other one was the modeling of the Nile from its sources to Aswan. And that was a really interesting work because I involved several groups, including End O'Connell's in Newcastle, and groups in Egypt, and also people from the administration, the Water Master Plan of Egypt. From that, the idea of working into systems analysis came to my mind, and I worked a lot in trying to put together several issues, economic and technical.
Talking about systems analysis and water distribution systems, you have been very active in use of modeling and optimization related to the field of water resources systems in general. Could you please discuss how you have used that systems analysis background in the field of water distribution systems analysis and the contributions you have made in the assessment of resilience and modeling?
Well, sometimes after I left IBM, because I won the chair of hydrology and water resources in Bologna, I started doing some research into the problem of minimization of costs. I always thought that optimizing a water distribution, a looped water distribution networks was meaningless, because the optimal network is a tree. If we don't put certain constraint, or we don't put a trade-off between something else and the cost. So I looked at the problem of not resilience, but efficiency. And I couldn't find something that was explaining overall, some sort of an overall index that could explain the behavior of the network. Finally, I went back to the work I did to determine GGA, the global gradient algorithm. That is, start from the energy. If you minimize, well, something related to energy, which is the content derived by Collins, then you have an indicator that is much more interesting than discharge at nodes or pressures and that. So I worked out some sort of ratio between the full energy that comes into the network and what we dissipate inside. In fact, the amount of energy we dissipate inside means the more we dissipate means a reduction of cost, because we reduce the diameters of the pipes. But in reality, what we are interested in is to create additional loop and additional flows, because if one pipe breaks, we need that the water reaches the same point through a different path. So we have to trade off between cost, which is linked to increasing the energy dissipation, and resilience, that is, provide the maximum energy outside the network. So it came out to be an interesting indicator of a natural behavior of the network.
In your long, illustrious career, you have collaborated with a number of people nationally and internationally on a wide range of interesting and creative work. Can you tell us about those relationships and your work together, and what made it exciting and productive?
Well, first of all, when I arrived in Bologna as a director of the Institute of Hydraulic Construction, I found out that there were many young people that had very little publication. So I tried to involve them into the research, and Pilati is one of them, who gave an interesting contribution to the final paper. We presented actually here in Leicester in 1987, when Brian Kuhlbeck organized the first conference, CCWI conference. And then Enda O'Connell, as Saldariaga mentioned, asked me to support him with a student of his, because he was not very in the problem of water distribution networks. So he asked me to help his student, and I collaborated with his student, who came out to be a very good guy, who has developed a lot. He has extended GGA to the pumps, to all the non-easy things like pipes and nodes. And then one of my students, Marco Franchini, became professor, and he is now heavily involved in water distribution systems. And you know, my work in Italy was not very well recognized, in the sense that everybody used CROSS everywhere, and so only after Lou Rossman created the program EPA Net, they discovered, funnily, that someone had developed the algorithm which was behind the program. And I must say that only few very bright guys, young guys at the time, took the lead on the GGA. One is Orazio Giustolisi, the other one is the group of Bruno Brunone, and I must say now it's going very well. I have contacts in various parts of the world. I had contacts in Germany, in China. People ask me to help them and to support them in their research.
That's very interesting and leads me to the next question, and that's your involvement with the industry and how that interaction led to some of the work that you've been doing.
Well, my interaction with the industry has not been very successful, I must admit, because the industry tends to solve specific problems, and particularly in Italy, they don't want to spend much money on research. They tend to spend more on replacing pipes or finding where the pipes are, broken pipes are. But doing proper research on water distribution system, it starts now. Now they have the problem of leaks, which has become a tremendous problem in Italy, and they are finding the need for assessing where the leaks are. So I have contacts with young guys who have established companies who are trying to prepare packages for the industry to find the leaks and to define which are the best monitoring network that will lead to an identification of the leaks.
Thank you. Finally, I'd like to ask you if you can give us the benefit of that experience that you have by looking forward to next 20, 30 years. What do you see as research opportunities in the water systems and water distribution systems area in particular?
Yeah, I think I have a clear idea of what we should try to do in the future. The basic issue is the fact that we are mostly engineers dealing with water distribution systems, and our view has been in the past mostly deterministic. Now we have to change this into a statistical view, in the sense that we have to not only assess what is uncertainty, but use it. First of all, we have to change the term. The term uncertainty is very bad to be communicated to the end users, because they only understand that we are giving them an upper and a lower band. But this is not the role of uncertainty, and we should think of it as knowledge. Knowledge is just the opposite of uncertainty. When uncertainty is zero, we have the full knowledge. Where uncertainty is total, we have zero knowledge. Now, the intermediate cases can be represented by a probability distributions, and the aim is to reduce the variance of these distributions and to identify the mean. So what we should do is to reformulate all our problems in terms of identifying the mean and reducing the variance, both for the state variables, including demand, which is one of the most unknown quantities, discharge in pipes, pressures at nodes, and also the conveyances. I'm not talking of resistance, but a conveyance, because we don't know the actual pipe diameter after many years of pipe in the ground. So we cannot separate the roughness coefficient from the diameter of the pipe. We must identify the overall conveyance on the pipe. And finally, if we are able to reduce the variance of all these quantities, then it would be possible to identify the leaks. Otherwise, we are fudging ourselves. So the other point is we have to aim at sustainability, because all these systems are mostly unsustainable. And we need to work towards sustainability in management of water distribution systems. Assessment of demand and control of demand. We must not allow people to draw water as they wish at any time, because if we do so, we will land up in searching for new sources of water, and the water availability is not scarce, but it's not infinite. So we have to go along these lines, and basically, in my opinion, we have to think in terms of knowledge. We have to communicate. Our probability distributions are not a measure of what we don't know, but are the measure of what we know. And if they are very concentrated, like delta of Dirac, then we know everything. But that, I think, it's rather impossible to reach.
Thank you very much, Ezio.
You're welcome.